Okay, I want to take a look at a couple of examples from start to finish of how these problems are more likely to look. So we'll look at 4 different situations, but again, you're not going to have to watch me work through every single one of these. Most will be for you to try on your own, and then you can look at it afterwards to check. So first one, y of x represents the population of birds on an island in year x. Y prime varies directly with the current population. Essentially, the more birds there currently are, the more birds there will be tomorrow. At the start of year x equals 0, there are 3 million birds on the island, and at the start of year x equals 4, there are 5 million birds on the island. So we're going to do a couple of things with this. First, we're going to obviously write the differential equation and connect it to slope fields and graphing solutions and the stuff we did already. And then also we will solve the differential equation. But before we get to solving it, let's see what we've got. I have 4 choices. We're going to look at these same 4 options for all 4 of our examples. So I have 4 slope fields, and there are a few different ways to choose the slope field that makes sense. One of those is really just based on the description that it's given, especially those 2 initial conditions. So x equals 0. I've got 3 million birds. I'm going to assume the y-axis is measured in millions of birds. And at x equals 4, there are 5 million birds. So one option, just for these 4 possibilities, one way of choosing the right one is just to see which one makes it easy to connect those points. So 0, 3, and then 4, 5. I'm going to put those points on each of these, or try to. Yikes. So bad at the surface, you guys. This is embarrassing. I know how points work. I just can't see because I'm 90 years old. All right. So just based on what I've graphed or what I've plotted, we can super easily eliminate 2 of these choices. If I look at option C, I'm going to eliminate that because if I start down here and I'm trying to end up there, basically any way I try to get up there, I'm going to have to cross through some of those tangent segments. Those tangent segments are forcing me downward, and that's not what the bird population does. So just thinking of the 2 points they gave me, that one doesn't work. The same issue happens with option D. The slopes, or the segments rather, their slopes are forcing me downhill as I move to the right, but I need to go uphill. So that one's out as well. So then it's between A and B. You could, if you're really, really good at judging these visually, you might make a choice based on that. Or we can think about what the differential equation actually is. So I'm going to leave it as A or B for right now. You might have a good idea already which one you think it is, but let's see. Y prime varies directly with the current population. So as we did a minute ago, let's do that one little piece at a time. Y prime, easy enough, varies directly. So that's k times something. And then this is where we have to be really careful with these word problems, is deciding which variable we're dealing with. The current population here is not x. The current population is our output, the y. X is the time, but that's not involved in the description they're telling us. So y prime equals k times y. So if I use my differential equation to decide between A versus B, if you haven't made a choice already, then this tells me, assuming that k is positive, which really isn't an assumption, it has to be, because all of my y values in these regions, all of the y values are positive, and all of the little segments have positive slope, so k has to be positive. So it's not an assumption, it's just a fact. So given, rather, that k is positive, this tells me that as y gets bigger, y prime also gets bigger. And even if k could have been negative, this tells me that as y gets bigger, then y prime, it's tougher to talk about it that way, but it does mean my segments would get steeper, just maybe with a negative slope. But here everything's positive, my y coordinates and therefore my k value. So as y gets bigger, the slope should get bigger as well. In A, that doesn't happen. For larger y's, my slopes are much smaller than they were. So B, by process of elimination, is the only good choice. And if we try to connect by following the slopes given to us, kind of matching the slopes as we get close to them, then we can connect those 2 points. So we wrote our differential equation, we chose its slope field, B, and then we sketched the particular solution. I did it just between the 2 points they gave me, but let's keep going, talk about what the bird population will do moving forward. Okay. So, same thing, same description at the top as what we had before, just recopied. Same differential equation that we wrote just a minute ago. And now let's actually solve it. And specifically, we're going to solve it. So we have this. There's going to be an algebra trick that we're going to use along the way, and there's going to be a really helpful calculus shortcut that we're going to get here. So even if you're skipping through my videos, don't skip this part. So we'll do it the long way just once, but this type of differential equation is a common one and a really important one. But let's do this the long way first just to see why it works this way. I'm going to multiply both sides by dx, and I'm going to divide both sides by y. I could move that constant of proportionality if I wanted to. I wouldn't bother. But there again, I divided both sides by y to get this to go away. That made a 1 over y show up. And I multiplied both sides by dx to get that to go away, which made this show up. That's the cat. So we can integrate both sides. And at this point, this is something that we've done for quite a while. Left-hand side, 1 over y, gives me natural log absolute value of y, plus a constant, but I'm just going to put that on the right-hand side. K is a constant, so its antiderivative is k times x, because it was a dx integral. And then my constant of integration, as we saw in topic A.2, I guess, I only need that on one side or the other. Also here, since we're dealing with a bird population, y is never going to be negative. You're never going to have negative birds. So I don't really need that absolute value. That's going to make my job a little bit easier. And so what I could do, I'm not going to, but what I could do is use my 2 initial conditions, 0, 3 and 4, 5. I could use those now to try to find the values of k and c. I'm not going to do that because of this algebraic shortcut. Also, I don't really feel like dealing with natural logs. So I'm going to go ahead and solve this for y. Getting rid of a natural log is something we've done a fair amount of. Hopefully we know by now that we just put everything on a base of e. Those are inverses, so now the left-hand side is just a y, and the right-hand side, at this point at least, looks like this. Here again, I could plug in my initial conditions and find the values of k and c, but I'm not going to do that. Instead, I'm going to use an algebra trick. So, same problem as before. This is the step that we are at right now. What I want to do, and something we'll do a fair amount of, and something that allows us to do this shortcut that we'll talk about in just a minute, the calculus shortcut, is think back to stuff we already know. So, kind of as a side note, if I asked you for 5 to the 4th power times 5 to the 7th power, think for a moment, the answer is not 5 to the 28th, but think for a moment about what you would get. Hopefully you got 5 to the 11th. Because this means that I have 4 5s multiplied together times 7 things that kind of resemble 5s multiplied together, and so altogether I've got 11. The point of this is to say that if I have 5 to the something, times, step ahead of myself, times 5 to the something else, then I can add the exponents. what we're going to do here is that same equation, but kind of in reverse order from what we typically did. If I'm adding exponents, as I am here, then what this rule tells me is that that's the same as e to the kx times e to the c. Take a second to let that sink in a little bit. What we just did is that if I'm adding exponents, that's the same as multiplying things with separate bases. And so then what I can do, c is a constant, right? And so e to the c is just some other constant. So I have e to the kx times some other constant. And writing that in kind of a simpler way, I'll just put that constant in front. This is going to be easier for us to work with because now my second unknown, the k and the c, or now the k and the d, my second unknown is out here by itself, which is going to be easy for us. And what that allows us to do is a calculus shortcut that you get to use from here on out, but only in a particular type of case, a very special type of differential equation. If you have a differential equation that's in this form, dy dx equals k times y. That is super important. K times x isn't going to work. But this says the rate of change of something is directly proportional to the amount of that thing. The rate of population growth is directly proportional to the population. If you have that, then from here on out, you are more than welcome to jump directly to what we just found, d times e to the kx. Or if we hadn't bothered with all of that individual or in-between work, intermediate work, you just have an exponential function, basically. Well, literally. So I have some constant in front, a base of e, because calculus really likes bases of e, and then another constant up here that kind of determines the rate of growth. So you are more than welcome to make that jump directly from here on out. And so now I'm going to go back and actually solve the bird equation. Okay. So from now on, what you'll be able to do after you realize this is your differential equation, you won't have to do any of this work that we just did ever again for that type of diffeq, and you can jump straight to y equals c times e to the kx. At this point, I am going to finally use my two initial conditions. I have to give you two because we have two unknowns, a c and a k, or a d and a k. So 0, 3 and 4, 5. I could start with either of those, but something that has a 0 in it is probably going to do some nice stuff, so I'm going to start there. The population is 3 when the year, the x-coordinate, is 0. E to the 0 is just 1. And so sure enough, this gave me a really nice thing. Already I know that that c is 3. If we had kept it in this form, then that c is a lot nastier, that k is a lot nastier, and your answer is going to look a lot worse. But we have this, so now let's use the other. At this point we know y equals 3, e to the kx. So let's go in and use our other initial condition. Let me change colors on that. 4, 5. So 5 equals 3 e to the k times 4. So 5/3 equals e to the 4k, and so we have to solve an equation similar to those we have solved before, and we're getting better at these, and we'll keep getting better at these. I need to get rid of an e, so I'm just going to take a natural log on both sides to get that to go away. Forgive me for running out of room here. Natural log of 5/3 is 4k, so k is 1/4. natural log of 5/3. And then I have everything I need. Y equals the C value, which we found earlier, times E, the 1/4 natural log of 5/3 times X. The parentheses here are helpful because they show me that this X is not part of that natural log. There are some algebra tricks we could do here to deal with the E and the natural log. I'm not terribly concerned about those, so we will stop that one there. So the birds problem we worked through from start to finish. Here again, I'm going to stop this video. That seems like another good stopping point, and the other 3 examples we'll go through a little bit faster. So looks like there will be a third video. See you there.